This is Math 251, and we're looking at section 12.5 called the chain rule for partial derivatives. Now, if you're thinking, hey, I've already been using the chain rule when I was doing my partial derivatives, that is actually true. You were using a version of the chain rule that was kind of adapted from the Calculus 1 version. Here what we're talking about, though, is true compositions of multivariable functions. So this is a bigger chain rule, I guess you might almost call it. Essentially what's happening is this. Think about a dependent variable that depends on two or more intermediate variables, and in turn, those intermediate variables depend on other independent variables. So you've got that intermediate stage between the independent and the dependent. It's really helpful to visualize the composition relationships using a tree diagram. So I'm going to start by just sort of showing you what I mean by those relationships and drawing the tree diagrams that we're talking about. So in the first example, imagine that you have sand slowly being released from a chute and forming a cone-shaped pile. So your sand dripping down, right? Forming this conical pile. All right, I'd like to know something about the volume of this pile of sand. And of course, we all know that the volume of a cone depends on both its radius and its height. So the volume of the pile depends on R and H, radius and height. Now, as the sand drips down, that radius is going to increase over time, and so is the height. So the radius depends on time, and the height also depends on time. To show this relationship as a tree diagram, I'm going to start with my volume and say that depends on both radius and height. And then radius depends on time. Height also depends on time. So that tree diagram just shows the relationships, the dependency relationships between the variables. Let's look at one more example like that. In number 2, a company manufactures boxes of cereal. The materials cost of production, so basically just what does it actually cost them, not the labor or anything like that, just the actual materials. What does it cost them to put out a box of cereal? I'm going to say, first of all, it's going to be the cost of producing the box and the cost of the cereal. So let's see, B, cost of the box, and C, cost of the cereal. All right, what do the cost of the box and the cost of the cereal depend on? Now I'm going to be a little bit simplistic here, and I'm going to assume that we're going to fill this whole box up. I know cereal never fills up the whole box, but for our purposes today, we're going to assume it does. So as I think about my cereal box, the cost of the box would depend on the surface area, right? The bigger the surface area, the more cardboard you have to use, and therefore the more it's going to cost you to make the box. Now, of course, the surface area depends on the length, width, and height of the box. So I'm going to say the cost of the box depends on length, width, and height. The cost of the cereal, what we're calling C, again, assuming we're going to fill up the whole box, depends on the volume. But in turn, the volume of a box also depends on length, width, and height. So, the materials cost of production, let's call production P, depends on, first of all, the box cost and the cereal cost. Those are my intermediate variables. But then the box cost depends on length, width, and height. And the cereal cost also depends on length, width, and height. So there would be my tree diagram that demonstrates the relationship between all of those variables. All right, Ultimately, our goal is going to be to try to figure out rates of change of the highest level, the p here or the v in example 1. So eventually I need to figure out how to do derivatives of those things. And so I'm next going to talk about how to use a tree diagram to write a chain rule formula for taking derivatives. All right, so if we want to find rates of change of these dependent variables with respect to one of the independent variables, not the intermediate ones, but the independent ones, it's often more efficient to use a derivative rule for compositions rather than trying to substitute and end up with huge, horrible, messy problems. This derivative rule is called the chain rule, and it's not one that I can write out a single formula for. It's one that you'll have to adapt to each situation. To adapt that chain rule, you're going to use the tree diagrams that we were just practicing. So let's go back to our sand problem, where we said the volume depended on both radius and height, and then the radius and the height both depended on time. Ultimately, I'd like to find a derivative rule for the rate of change of the volume with respect to time. So what I'd really like to find is the derivative of v with respect to t. Now you might be thinking, hey, wait a minute, she just used a regular d, not a delta here. Notice that eventually v only depends on one variable, t. So I actually didn't need a partial derivative on that one. All right, so how do we get there? What we're going to do is we're going to follow every possible path from v to t, starting with this one. Along that path, I'm going to say that my derivative is equal to, first of all, the derivative of v with respect to r. Notice that that is a partial derivative since v depends on two variables. And then I'm going to multiply along the same path, dr dt. I used a regular derivative there since r only depends on one variable. Plus, I have another path that goes from v to t, this one right here, and I'm going to do the same thing there. The partial derivative of v with respect to h multiplied by the derivative of h with respect to t. That would be my chain rule formula to get the derivative for this particular diagram. Again, the chain rule formula is going to change based on your diagram. Let's try the other one that we did, the one about the cereal. With the cereal, we had said that the cost of production depended on cost of the box and cost of the cereal. Cost of the box depended on length, width, and height, and cost of the cereal depended on length, width, and height. So, right now we want a derivative rule for the rate of change of the cost of production with respect to the width of the box. So we're being asked to find the partial derivative of p with respect to w. All right, so again, I need to follow every path that goes from p to w. There's one right here. Partial derivative of p with respect to b times the partial derivative of b with respect to w plus this path here, the partial derivative of p with respect to c times the partial derivative of c with respect to w. And there's my chain rule form for that particular setup. All right, so if you're getting the idea of how we create these chain rule formulas, let's take a look at a couple of specific examples now. In example 3, we've got this function z as a function of x and y, And then I've also got x as a function of r and s, and y as a function of r and t. So the first thing I'm going to do before I even try to do any derivatives is set up my tree diagram. My function z depends on x and y. X depends on r and s. Y depends on r and t. We are asked to find the partial of z with respect to s, and then the partial of z with respect to r. So let's start with partial of z with respect to s. There's actually only one path that goes from z to s. It's right here. That's it, right? So the partial of z with respect to x times the partial of x with respect to s. And then I'm just going to come up here and do those derivatives. Z with respect to x would be 1y minus 2 plus 0 times the derivative of x with respect to s. Let's see, that'll end up being a negative sine s, so negative r sine s. And that's really it. I could clean it up just a little bit. Maybe I'll bring my negative out and distribute it here. So I'd have minus y plus 2 sine s. What about the derivative of z with respect to r? Well, now I'm going to notice there's actually two paths to get from z to r, right? So we'll have to account for both of them. This first one would be the partial of z with respect to x times the partial of x with respect to r, plus this one, partial of z with respect to y times the partial of y with respect to r. So let's see, what have we got? Partial of z with respect to x, we actually already did that one once. That would be y minus 2. And then x with respect to r, the derivative of the r is just 1. Cosine s is a constant. Plus partial of z with respect to y, that would be x, 0 plus 3, times the partial of y with respect to r. Again, the derivative of the r is just 1 times the constant, cosine t. And I don't know if there's really anything I can do to make that a whole lot better, so I'm just going to leave it like that. All right, let's try example 4 here. Here w is a function of 3 variables, x, y, and z. So let's start our tree diagram. X is a function of a and c. Y is a function of b and c. And z is a function of a, b, and c. Our goal is to find the partial derivative of w with respect to c. Now there are 3 paths that take me from w to c. There's one there. There's one there. And there's one there, right? So I'll have to account for all 3 of them. First one would be partial of w with respect to x, and then partial of x with respect to c, plus the second one, w with respect to y, times derivative of y with respect to c, and then the third one, w with respect to z, times the derivative of z with respect to c. So a bunch of derivatives to do here. Let's see here. Come down here, we have a little space. W with respect to x, I'd have 1/2 times all of this to the negative 1/2. And then my chain rule here with respect to x would give me a 2x. And then dx dc, a times 1, or just a. All right, w with respect to y. Very, very similar. My chain rule this time, though, would be a times 2y. And then dy dc would be 2bc. Plus, this last one, w with respect to z, chain rule on that one will give me a times 2z. And then the derivative of z with respect to c would be a squared b squared just times 1. A squared b squared. All right, this is not going to get beautiful, but we can maybe make it just a little bit prettier and get rid of all these 2's for starters. And let's see, this is going to be xa, or ax. And notice that that negative 1/2 power is part of every single term, so I'm just going to go ahead and put that as a common denominator. Square root of x squared plus y squared plus z squared. So that's taken care of. This would be a plus 2bcy. And this last one would be a plus a squared b squared z. And so there's my derivative. All right, we will come back and look at just a couple of applications in the second part, or the video for the second part of this section.